Today we'll be looking at two important topics. One is full text indexing and searching of documents, and the other one is a more general concept of how to be nimble and incremental, which is an amazing capability to have. So full text indexing and searching of documents using Neo4j, the graph database, or possibly other graph databases. Today we'll be discussing the current capabilities that are found in the latest release of the open source project BrainAnnex, which is a Python technology stack for graph databases. We'll be discussing the synergy between graph databases and ontologies. You can think of ontologies, if you're not familiar with the term, as categories that are interlinked. At the same time, we will discuss how easy it is to add new features. And here's the catch. When one is in full control of the entire technology stack, that's the part that's easily overlooked. Of course, being nimble and incremental is not at all limited to graph databases. However, graph databases do help because they inherently lend themselves to being nimble and incremental the way other technologies, such as relational databases, don't. But it's only when we combine graph databases with the full control of the entire technology stack that one can attain a state of being really nimble, incremental, and at that point it becomes ridiculously easy to add new features. So we'll demonstrate that. But at the same time, we will not get too technical. We'll be looking under the hood a few times, but the presentation will be at a high level. Full text indexing and searching. We have some documents and we want to be able to locate the document of interest quickly and with least fuss. I will be demonstrating, as I mentioned, the current capabilities. So let me scroll out here. This is a web app that currently implements some of these features I was talking about. Let me make a brief side tour without getting too technical. Let's talk about the technology stack. And there's nothing particularly unusual about this technology stack. It's a very standard way of doing web apps. We have a graph database. We'll be using Neo4j, but in principle could be other ones as our bottom layer. And then we have a number of modular core libraries that perform fundamental foundational operations to help manage the database and schema layer and so on, things I discussed elsewhere. And then we have a set of specialized libraries, and that will be the focus today, including full text indexing. And then using these libraries, one can implement a web API that is a server that waits for requests over the internet and response. On top of this web API, one can build a web app that contains things like a control panel and features to upload and present and the user interface and anything you want to do. All these parts are modular, so if you have an interest in using the existing open source software and libraries, you can pick and choose whatever you want and need and adapt or fork and personalize to your own use case, anything that you have an interest in. For today's presentation, we'll be using the web app as our user interface. So here we are running this web app. We are running it on a local computer, and the graph database is on a server in the cloud. It's not the topic of today's talk, but you can run it and you can have the app and the database in the cloud, both, or you can have the app locally in the graph database in the cloud, or you can have both locally, but it doesn't matter for today. So let's start with an exciting document to index. How about a document with some kind of catchy word that we won't find anywhere else? I located Julie Andrews' song, the Supercalifragilisticexpialidocious song. So that will be a good word, a fun word to search for. And this is the lyrics of that song. I have it as a text file. I won't be explaining how to use this web app. It doesn't matter for today. Let me just upload that text file. So this text file has been uploaded, and there it is. It's stored in the web app. The web app implements a multimedia content management system. It's just one of many use cases that one can implement with the technology stack. And this use case comes out of the box with the open source BrainAnnex project. It's just one of many use cases that could be implemented. There's a document. We can click it and there it is, looking at the document. So let's try searching for it. So let me go under the search. What I will be discussing is existing search capabilities as the app is today, and then I will discuss how to add some features, and I'll demonstrate how easy it is to add a few features. There's some limitations right now, primarily due to the fact this part of the web app is pretty new, and we can just search for one word. We'll discuss later how to overcome this limitation. So let's look for, I'm not going to type the whole word, supercali. And lo and behold, it located the document, which is a text document that inside contains a word that contains that string supercalif. The way the search is implemented right now, it looks for any word that contains that string we pass, and then locates any document that contains that word. Let's look at that song again. I should say that I have a number of documents already uploaded because this is my work version of the web app I use for my own personal use case. But not surprisingly, searching for a specialized word like supercalifragilisticexpialidocious is not the word I'm using in any other document I upload it to the system. How about looking for a word that's more common, like dismay here? Let's see what happens if we search for that word. And once again, this is not a fresh install. This is a system I've been using for years. I found 3 results. One, again, is the Julie Andrews song. As we saw, it has the word dismay. And the other 2 are 2 other documents. One is a document about the basics of UX design. And this is a PDF document, and if we do a search for the word dismay, indeed the word dismay occurs here. The other document here is a booklet for a course I took about inventions that changed the world. So let's double check that the word dismay is indeed in that document. Lo and behold, there it is. We have done what we set out to do, searching for words in documents that had been previously stored in the system. So you might say, could we get a snippet here? And the answer is, well, not currently, but that's a feature on the to-do list. We will not demonstrate that feature today. I'll talk about the ease of implementation of 2 other features. Right now, there is a table of contents that shows the name of the document. Let's take a closer look at the results we found. So we searched for the word dismay and we came across 3 documents. But let me point out something else. Here in this UI, it's being called links. You can think of this as tags, that each document is attached to a particular tag. Here, the tag is a demo of full text search, which is a category I created just for this video. This one is UX design, and this one is multiple tags. One is books and ebooks, one is science, engineering, history, and one is history. In a very first approximation, you can think of these as tags attached to documents, but in fact, it's more than just text tags. These quotes tags are actual entities, which means there is properties about them, and in particular, there is a set of relationships among them. You can think of that as categories, as subcategories, or you can call it ontology. And if I click on any of these, and this is just the way this UI is set up to work, I can see all the documents that are linked to this tag. So here the demo of full text search brings me to this page I prepared for this demo, which contains just a formatted text document, which is basically HTML document. It now also contains the document with the Julie Andrews song, as you can see in the listing on the left top. More interestingly, if I click on the UX design, it takes me to everything that I currently have in this information management system that's labeled with this tag UX design. And right now I have a series of bookmarks to websites, and then I have some images, some HTML documents, which you can think of them as formatted text. I have PDF documents. So these tags I'm talking about the ontology, they're interlinked, and that's the strength of what that makes them an ontology and not just simple text tags. Let's take a look at them. I said this video wouldn't be too technical, but we will look under the hood once in a while. Here I'm using a tool that's not meant for end users. This is meant for data engineers, and it's called the Neo4j browser, that allows you to look into what's stored on the graph database at a low level. The tags I was referring to are called categories inside this implementation. And let's see how many we have. So here I'm issuing a query. Don't worry about that. It's just a command that experts can use to retrieve information from the database or to update the database. So I have a little over 1,200 such categories I created in the past. And there's a handful of them that, as I mentioned, this creates an ontology. This is just a handful from those 1,200 we saw before. This is a top level category home. Under it there's languages, and the languages there's French, English, Brazilian, Portuguese, Italian, German, all languages I speak or have studied. Under German there is more subcategories like German pronunciation, German numbers, date, times. As you can probably guess, German has been more on my mind in recent years. And the subcategory of this creates a tree, but it doesn't have to be a tree. In fact, it's not a tree. It happens to be a tree in this example, but generally speaking, it is a graph, hence the name graph database. Graph meaning a mesh, a network. In a graph, a particular node, a node represents a record. The items here in blue, you can think of them as records in a spreadsheet. Here they're shown round, but if it's easier to visualize, think of them as rectangles, lines, rows in a spreadsheet. And so the tree relationship is similar to the way in a book you have chapters and then sections, subsections, and so on. But it's more general than that. You could have situations where a particular item is attached to more than one parent category. And in addition to the main ontology, you can also have other relationship. Like here I have a see also relationship between English and quotes. Quotes, strictly speaking, is not a subcategory of English because some of the quotes I have are from other languages, but most are in English, so I created this see also relationship. We'll go back to ontologies in the last part of this video when I discuss enhancements and how easy it is to make enhancements to the search results. So here I'm again showing those three search results, and let's take one other brief under the hood peek at how we get from the word dismay to finding these three documents attached to it. For those of you who are more technically inclined, there is a series of articles I wrote that's been expanding quite a bit lately, and it starts as a tutorial of increasing complexity and then a series of special topics. One of them is a full text search with the Neo4j graph database, which is what we're talking about today. Other things include visualization and so on. So let's look at this. And here is the technical details as well as overview, but at the more technical level of what we've been talking about today. This image here is what we'll be revisiting shortly. The magenta pink nodes are individual words, sort of like the word dismay we searched for. The brown nodes are just intermediate internal nodes for the implementation, and the blue cyan nodes here are the documents. In the process of the search, we go from individual words to finding documents that have some kind of a relationship to those words. Don't worry about the part of the top schema. That's technical detail that won't concern us today. So let's find this connection for the search we just did. So here's another look under the hood at the database. Here at the top is a query in a programming language called Cypher, and to many people it will look complicated, and this is not the topic of this video, but anyone who's a data engineer will find that this query here is ridiculously easy compared to how we would be doing this in something like a relational database, because basically here we're asking to go from a word whose name contains the string dismay, and then traverse until we find a node that represents a document. And the database with this query language does all the figuring out for you, so you can ask at the high level what you want to do and let the query language parsing and the graph database figure out for you. So that's the result. So notice that we are finding two words, dismay, but we're also finding dismayed. And this is just the way the search is being implemented right now in our system. There is no law that it must be done this way. We could enforce exact match, for example, but it just suited my needs and may be good for many use cases to have it this way. Whenever we search for a particular word, we also automatically by default search any word that contains it. So if I search for dismay, I'm also searching for dismayed, so I don't have to worry how I conjugated it or what grammatical change I made to it. And let's look at the documents. So that's the Julie Andrews song, and here's some metadata about it. This is the basics of UX design, that ebook, and this is the ebook about inventions that changed the world. Notice that this last document here does not have the word dismay. It contains the word dismayed. Remember that paragraph about the inventor who was dismayed by something. And so as long as we do a search for a stem or any substring really, we automatically find any document that contains either that exact string or any string that contains it. Here I expanded the diagram a little bit to show you some more records in the database, namely some of the blue nodes connected to the green ones, the blue being the categories or ontology, just a handful out of the 1200 I showed earlier, and then these three are the documents. So here we can see the Julie Andrews song is only tagged in this special purpose category called the demo for the full text search. You can see the full name there. And then this is that ebook about the basics of UX design, and it's tagged to that category UX design. And likewise, this is the book on inventions that changed the world, and it's tagged to three categories. One is books and ebooks individual, the other one is science, engineering, history, and the third one is history. And in turn there is a relationship of subcategory between science, engineering, history, and history. So why is this tagged in both? It's just a convenience out of desire to make this document appear whenever looking at the whole history. This you can tag any way you want, but the more you tag, especially to specific categories, the more that can aid the search. That's something we'll talk about later in this video. Here I made the query to the database a little more complex. I'm not going to explain it in this video, but basically I'm following links to the categories and then the subcategories of the star means any number of relationships. So what here we ended up doing was the part I showed you before, which is approximately this part, and then we're following the entire rest of the tree, the ontology tree. Well, this part is a graph really, but many people find it easy to think of it as a tree. So for example, the history is directly attached to the home, which is the root category. Likewise, that demo category I created just for this video is just ad hoc category attached to the home, and I'm going to delete it as soon as I make this video. But legit categories like UX design currently is a subcategory of internet web publishing, which is a subcategory of both computer science and networks, and computer science is a subcategory of science fields, although I have it attached to home as well to show up at the top. Science fields is attached to science, math, engineering, and so on. Details don't matter here, but the point I want to make is that this is one part of an ontology, a small part. Remember, we have 1200, or I have 1200 items in this ontology, and here I'm showing just a small part that's basically the parents of the tags that these 3 documents we found in our search, traversing from those categories all the way to the root category. If we were to look at the whole ontology I have, it's going to be a lot more complex. Let's go back to a higher level. This has been a simple search, but let's say we're looking for something like marine biology. And once again, this is not a new install. This is a system that contains a lot of data. At present, we can only search for single words. This is a limitation that I will overcome here as part of my demonstration video, but currently it is a limitation. So if I want to search for marine biology, I can only search for one word at a time for now. Let's search for marine. Let's see what we find. And here I have 19 search results for marine, including a course on geological wonders. And here this is a formatted text note about boating, as well as notes about geographical information systems, and something about sun lotion. I don't know why the word marine is in that, maybe an ingredient. Something about physics and history, all kinds of stuff that just happens to have the word marine or a superstring of marine. So this is too broad a search. We really want to do a search for more than one word. So then when we search for marine biology, we find more relevant search results. So here we're at the second main point that this video is about: how to expand the existing system and add new features. This is not a technical video, so I will not discuss in detail how to do it, but I will measure how much time it takes me to make this change right here on the spot, and I will report back. Let me just talk at a high level what needs to happen here. Here, instead of a single word, this will need to accept multiple words. So if I look at the technology stack, I need to change something in the UI interface to allow that to send all the words to the web API, the backend. But most of the change will be here in the web API, the backend. I need to make sure that it will accept a string with multiple words. I need to parse those words and then make use of the specialized libraries to find all the results for each of those words. The heavy lifting is basically done already in the specialized libraries. I just have to do a little work in the web API to do that parsing, and then to put the results together, and that shouldn't be too hard. So let me do it, and I'll measure myself how long it takes me to do this. I'll be back. Okay, I'm back. The feature I promised is now implemented, and it took me only 1 hour and 3/4. So it was a breeze, as I anticipated and as I promised. I'll discuss it in a second. But first, let's try it out. Notice I changed the wording there, and let's start by the same search we did before, namely marine. And again, we get the same 19 search results, maybe in a different order, but the same ones. So now let's search for marine biology. And voila, we have restricted our search to 9 results. Let's take a look. Here on the left, there is a table content. So a very straightforward one is this HTML note that has the words marine and biology. But what about other items? Why is there Mysteries of Modern Physics and other documents about physics, history and inventions, machine learning, theoretical computer science? Why are they still showing up under marine biology? Let's take a look, and that will give us some insight as well. This is a PDF document from an online course. Let's do a search for marine. Voila, marine is indeed there, the marine chronometer, and in the context of history of timekeeping. So the word marine is there. How about biology? Yeah, the word biology is also present. So the search result did the right thing, but at the same time it was dumb, basically. And that's what we'll address in the next enhancement. Our search function is vastly better than it was before. There's still ways to go, but there's a vast improvement of being able to search for multiple words. Let me point out there is a design decision I made during the implementation that now the searching is requiring all the words to appear. So if we're searching for marine biology, we get only the results that have both words. What if we wanted to find partial matches? Yeah, that would be another easy change to make, and I will probably make in the future, but not this time. Now let's implement one last feature, and once again I anticipate it will be fairly easy. This new feature will address the fact that when we do a search for marine biology, as we saw earlier, we get many documents that have nothing to do with marine biology. Why is that? Well, let's try something else. Let's search for a word that's used by many sciences, entropy, and let's see what happens. Here I'm getting many results. Some of these results, like this HTML document, is from machine learning, more machine learning, physics, thermodynamics, so chemistry and physics, and that is really the root of the problem, that a term like entropy is used by various fields, and when we do a search just by words, we are not addressing the semantics of things. We are just matching strings and not taking into consideration meaning, and that's the same problem we had earlier with marine biology. We had search results that indeed had the word marine or a superstring of it, and also had the word biology, but they were not particularly, in fact they were not at all, about anything specifically marine or anything specifically biology. So what we want to do now is instead of doing searches across the entire set of documents, we want to restrict those searches. Well, one particular design would be to restrict searches to anything that's tagged with a particular item from the existing ontology. A possible design would be in this search page, there would be a pull-down menu, and when you do a search for the same search we already have for one or more words, however, we will restrict the search results to be linked to that particular ontology entry we picked, or you can call it category if it makes it easier, or to any subcategory of it. So, for example, if we're doing a search for marine biology, we might want to restrict to biology if biology is one of the categories in the system, as it is in this particular database. And that will eliminate results from physics and other random topics that just happen to have the words marine and biology in them. Likewise, entropy, are we interested in chemistry or physics and so on, we will restrict the search. Once again, I'll roll up my sleeves and implement it, and I'll get back to you as soon as it's ready and let you know how long this takes. Well, hello again, I'm back. Did you miss me? So, how long was I gone? Turns out I knew it would be more complex than the previous enhancement, but turned out to be relatively easy. It took me just 2 3/4 of an hour, and that's it. I mean, I knew it wouldn't be particularly long, but nonetheless, it was a pleasant surprise to confirm how easy, almost ridiculously easy it is. So let me demo it and then explain a bit why it's so easy. Where we left off was that we expanded our search function from just looking for one word or superstring of to searching for multiple words. And that was good, but still left a lot of problems. For example, when we searched for entropy, we found a whole bunch of results, a whopping 36 results, and some of them are physics, chemistry, computer science, machine learning. So let's go back. And now, as you probably noticed, I changed the user interface here a little bit. In particular, this I've forgotten to mention documents here. That was an omission because in the early designs it was only notes. The term notes is used here to refer to HTML documents. So anyway, I added a menu here, and this menu has all the items in that ontology I've been talking about. Now, instead of searching for entropy throughout all the nodes in the knowledge base, we can be more specific. For example, given that entropy is used in different sciences, maybe we're interested in physics. Lo and behold, I happen to have a category in my ontology called physics. And let's see what happens if we do a search from, voila, only 2 results instead of all the many results from earlier. And the first one is from this course about physics of time. That's definitely physics. And the other one is from a PDF on a physics course. So we're good. This is all physics related. And what about marine biology? That's something we had problems with earlier, that we were getting results all over the map in random documents that just happened to have the word biology in marine, but had nothing to do with marine biology. So I'm trying again that search result that was incomplete earlier. Voila, now it works as expected. That's a conference on longevity science, and let's double check. Why is the word marine there? It just happens to be the name of the hotel, so that's not particularly insightful. The word biology, of course, will be here. This is about longevity science. So restricting to biology was not tight enough to weed out this particular entry here. And now there's this document here, which is located because it contains the word marine, it contains the word biology, right there. And it's attached to a category, this course oceanography, which is a descendant of the biology category in our ontology. So how was it possible for me to make this fairly big change in features in only 2 3/4 of an hour? Let me give you a quick rundown. And I made a few changes in the UI. Bigger change was in the web API and also in the page generator. The template which is used to generate this page now needs to provide that list of all the categories. So that's a change I had to make. And then I had to make changes in the UI here to provide this menu built on that data. And then in the web API, I had to make some changes to accept that category as part of the search request and pass it forward. But the biggest change was in the full text indexing library. And this is where Neo4j and its query language cipher saved the day. It turns out that restricting the search result to documents which are linked to a subcategory of a given category, it's a pretty complex concept, but it's done very, very easily thanks to the power of the cipher and the graph database. I did 2 searches to show you some debugging information that is insightful. This is the search for entropy without restrictions. And don't worry about understanding the query, but the point here is that we have a particular query that we pass to the database, searching for words that contain entropy. So remember, we're looking for a string or superstring of it. Now let's look at that same search when we have a restriction. So now we are restricting the search for categories with this URI, and the query looks similar, and it is. So this part is the same, and the new part is this one. What we're doing here, and don't worry about details, is that those content items that we found in the unrestricted query earlier, now we want to make sure that those are linked to some category, and that category is a subcategory of some other category, where that some other category is the URI we're trying to restrict to. And the star 0 ... means 0 or more links. So basically here we're following a path through the graph, a number of hops that could be 0, 1, or any number, until we get to the category that we're restricting to and its descendants. So all this navigation is pretty complex, but we're not doing it. We're just passing it on to the graph database and say, do it for us, and it does. That's why I was able to make the implementation of this kind of fairly big feature enhancement in less than 3 hours, because the heavy lifting was done by the powerful query language, and then above and beyond that, I am in full control of the entire technology stack. So that's the point of this video. The features we had at the beginning of the video. Now we have 2 more features, but more importantly than that, I hope I've impressed to you the fact that now we have a platform that allows new features, even fairly complex one, to be added fairly easily. And the key element to do that, once again, is a powerful graph database with its powerful query language, and our full control of the entire technology stack.